Alright, here's a video 2 where we're going to do a quick review of the inverting op-amp characteristic V over VI derivation. Okay, and this will just serve the purpose to review how we analyze op-amp circuits having negative feedback, and we will not be analyzing one with a non-inverting one. We'll just use this as our example. So let's say that we have, this is set to, so we'll make it a little more interesting, so we'll call this VP here instead of grounding the non-inverting input. Let's say we have R2 and R1, and we're going to find what is VO as a function of VI. Now we're going to do this first for the case where the gain, the open loop gain, is infinite. Now recall that in general the op-amp voltage output is going to be some open loop gain, AOL, times V plus minus V minus. Those are the two inputs to the op-amp. And we can label the differential voltage delta V, and where we can rewrite now VO as the gain, the open loop gain, times delta V. For an ideal op-amp, this is going to be infinite, and we're going to assume that in this case. So we could also write then delta V is equal to VO over AOL, which is therefore going to be equal to 0 for any finite VO given an infinite AOL. Okay, so that's where we arrive at the V plus equal to V minus. This is only for negative feedback, right? Exclamation there, right? Only for negative feedback. Okay, so how do we analyze this? The way I like to set it up, let's do it we'll do it both ways. We'll do KCL. Where would we do KCL? We'll do KCL right at this node here, the inverting input node. So we will have, we'll do currents leaving. So we'll say V minus VI over R1 plus VI minus VO over R2 is equal to 0. We'll say that V minus is equal to V plus because of the negative feedback and the infinite open loop gain, and that is going to be equal to VP, whatever this voltage source is. So now we just do some algebra, and we'll have 1 over R1 VP plus 1 over R2 minus 1 over R1 VI, and that is going to be equal to 1 over R2 VO. So now we can write VO is equal to R2 over R1 VP. Oh, sorry, I just found my mistake. This is not VI, as you all knew. This is going to be V minus, right? The current flowing out here is going to be through R2 is V minus VO. So now let's proceed. VP minus VI over R1 plus VP minus VO over R2 is equal to 0. And we can collect our terms. 1 over R1 plus 1 over R2 times VP minus 1 over R1 VI is equal to 1 over R2 VO, which multiplying through by R2 will give us R2 over R1 plus 1 times VP minus minus R2 over R1 VI. Okay, which is, I'll rewrite it one more time, as, well, I guess that is the formula you use, R1 plus R2 over R1 times VP minus R2 over R1 VI, okay, which we could have solved very readily had we had the two canonic forms of inverting and non-inverting amplifiers. We would have used superposition to turn off VI here, and then we would have a non-inverting amplifier with an input VP, or we would have turned VP off, and then we would have an inverting amplifier whose input was VI. And with those two superpositions, we could have arrived at the two terms that show up now in VO. Okay, I'll stop here, and then I'm going to rederive this now with the finite open loop gain.